Okay, so I think it's just about time, so I'll get started. Thank you very much for being here. My name is Bilar, and I'm going to talk to you about, well, the computer lets me. I'm going to talk to you about a common problem that we have when we want to identify and classify specific specimens of software. On the one hand, you want to do it quickly, but you also want to do it exactly. So you want to have your cake and eat it too. The problem with most approaches is that they either fall squarely on one end of the spectrum and on the other one. What I propose is just a modest approach. In German, you call it the Denkanstoß, which means something to think about. Namely, using statistics, which is a form of aggregation of data, some would even say a form of compression, that is a little bit more resilient to common obfuscation techniques, so that we can, with reasonable accuracy and reasonable speed, quickly identify and afterwards classify malware. So the idea behind the three approaches that I'm going to show you today is very handily represented on the state-of-the-art graph. On the lower left-hand side, you see signature-based approaches. They are quite fast, they're quite exact, but they're relatively sensitive to permutations. They're relatively sensitive to all sorts of these obfuscation techniques that you deal with. On the other hand, you have emulations and heuristics, which is, and I figured this out during my training, more of a black art than it is a science. You have to rely on a lot of implicit knowledge. I mean, you have to know this. It's hard to codify, and it takes you potentially a very long time to go through this. So what I'd like to find is a sweet spot, like Goldilocks. Not too cold, not too hot, but just right. Just the right amount of simplifications that we have a little bit more obfuscation tolerance, and yet we retain some of the speed that we've had before. And the vehicle with which I would like to explore this, I call statistical structures. No, I mean, you can call it whatever you like. I just wanted something that had some alliterative meaning to it. There are three approaches that I looked at. One was taking the perspective of the opcodes. We build a frequency distribution and build, from this frequency distribution, a fingerprint. The statistical structure there is the frequency distribution of the opcodes. I did it primarily through static disassembly, but there's no reason why you couldn't do this through memory, taking snapshots. The other one is the time-tested and true Win32 API call sequencing. So what you do is you observe the API calls, you put them in a call vector, in a vector space model, use a simple similarity function to compare them to other known families, and then you can classify them. Very simple model, had surprisingly good results, I have to say. The third one is graph-based. If you don't know much about graphs, no worries, I'll give you the 2-minute primer. The idea here is that programs can be represented through a very powerful framework, which is called a system dependence graph. It captures control, flow, and call functionalities in the graph, and we can extract certain features of this graph. And I'll talk about those features in a little while. Again, construct a statistical measure on it and try to use this for classification and identification purposes. This is the one-slide synopsis of the fingerprint analysis. In essence, again, you tally up the opcodes of the specimen that you have there. You build a statistical profile, and you start comparing them to, let's say, what I call goodware, because non-malicious software was too long to fit on the slide. Good software against bad software, and see whether you can find any discrepancies. Again, statistics are a nice vehicle because statistics are relatively robust under permutations. If you take, just as a very simple example, if you take the average of 1, 2, and 5, you get the same thing as the average of 2, 1, and 5, even though the order is permuted there. The main result I got here is that rare opcodes explain much more variation than the common ones, and I'll show you this in a second. A word about the procedure. I fired up my old Osborne 1, and I inventoried all the PEs, and there I ran them through. I took a random sample. I ran them through IDA with the customized instruction counter plugin, which also recorded some meta information. The important stuff on the slide is right around here. Gave me out the compiler. I wanted a few more factors. This I put in by hand. What kind of type of software it was. This is just my own taxonomy. The meat of the instruction counter is here. Gives you a ranking. The number of the opcodes. 20% were mobs in this particular program, and there were 2,000 of them found, push calls, and so on. I parsed this and then I fed it into Excel and did some statistical analysis on there. For the malware, I took a few more precautions because I listened to Jason Geffen and Scott Lambert, who told me always do this in a virtualization environment. So I did this in VM Player. I again ran it. The only difference I did here, as opposed to the goodware what I call non-malicious software, is that I fixed 7 classes. I wanted to also see whether there are signatures that differ across classes. So rootkits, Trojans, backdoors, tools, bots. I just assigned this malware to these 7 classes. Again, I did the same procedure, and I put the data into Excel. If we look at one of the first results, just this old pie chart. Normally I hate pie charts because they're a waste of ink, but this here shows you something interesting. So we're about 400 opcodes or so. We found about half of them. About 72 opcodes cover practically everything. 2/3 of all counts are covered in the first 5 opcodes, and 14 opcodes cover over 90%. And as you would expect, MOV is in there, and push, and call, and pop, and so on. This is for the good software. For the malware, and this was aggregated, and these were 67 Ps, this, again, class block from my 251, we have a similar picture. We have, in the top 5 opcodes cover about 2/3, where the top 14, over 90%, and the top 60, 100%. I found 2 undocumented ones, which then, in hindsight, showed me, rare opcodes do carry some information, but more of that later on. This slide, how do you parse this? You see on the outer rim, this is the aggregate malware. And on the inner rims, these are the class block ones. I don't know if you can see this from the background, but I anticipated this, and I have a zoom tool. So the second most outer ring is the worms, the third more is the virus, the fourth is the Trojans, bots, tools, then rootkits, user rootkit kernel. Okay? Now, from this slide, you should only take that. You see there are some discrepancies in the very common ones, but as we go down here, they seem to the distribution frequencies and occurrence seem to kind of converge here. Now, if I tally this up, this is completely unintelligible, but I just wanted to say what you get here. This is kind of breakdown. How do you read this? These are the top 14 opcodes, the 14 most frequent opcodes. This is my baseline, goodware, right, the non-malicious stuff, and this is for the other classes. And we can see here, they are the viruses used on average 16% were mobs, 22% were push, and so on, as opposed to goodware, 20% push, 8% were calls, and so on. The key here was that this is a frequency distribution. Now I would like to see whether I can run some tests on this and answer a simple question, namely, given that I have this opcode frequency distribution, is there any significant difference for malware in this kind of distribution? So I'm looking at the distribution of the goodware and the malware, trying to figure out, is there something other than chance that could explain discrepancies or similarities? So on the left there, you see my baseline. What I did was, for the statisticians among you, I did a contingency table test, chi-square testing with Huberin star residual test. What I got here, that's statistical thingamajig. How do you parse this? Well, it's a little bit hard to parse, and most of the explanation will come in the next slide. What you can see here, what you should get from the slide is just, I color-coded it for visual convenience. Whatever is darker means higher or lower higher or lower discrepancies. Whatever is white seems to be kind of similar. Whatever is darker red or darker blue seems to be different. So we can see here that the kernel rootkit, for instance, has practically everything. Everything seems to be significantly different from the normal stuff. Tools seems to be kind of, roughly, 2/3 and so on. Worms, for some odd reason, like that too. I don't know why. So what I showed you on the previous slide was there is, according to the tests, and again, it's a statistical test. This is not, the word of God coming through Moses. All this thing tells you is that from this test, this is what it tells you it's significant. There's another statistical test you can run. It's called Kramer's V. What Kramer's V, and this is the top line here, tries to say is, listen, okay, you figured out that there is an association between the column and the row variables, between the classes of software and the frequency distribution. But how much of the variation of the data does it explain? And what we find here from this slide is that just 5 to 15% of the variation is explained actually through this association. So this is not a very good predictor. So what you get from the slide is the top 14 opcodes, the most common opcodes, are not a good predictor to be able to say this piece of software belongs to goodware or to any of the malware specimens. I have here a few hypothesis why why I see these discrepancies that I see in the testing. People with much more knowledge than I do can probably figure out much better reasons why this is, but these are just my thinking on it. Sampling the horse from the other end. Let me look at the rarest opcodes. This is a sampling of the rare opcodes. They're so rare that I couldn't get them any more in percentages. I had to get them in parts per million. So these are samples, so this is out of 1 million opcodes, 37 will be FDIV-P, and 260 will be NOPS here, and 20. This is all from my samples. Again, I ran this. I did again the chi-square test with the star residuals. And what I found here is, again, the most interesting part here is, again, Kramer's V tells me that although I don't see in many categories a statistical significant deviation, and those that I do see, it does explain, anywhere between 12 and 63% of the variation, depending on where I am. This may be an artifact of selection sampling bias, or this may be a real effect. I'll have to investigate it further, but it conforms a bit to intuition that they try to be a bit evasive, have some instruction substitution, all these little obfuscation tricks that you learn from Eitam's book, or that you learn from Zohr's book on malware research. You may find this in there. Okay. So what I would like you to get from this first third is the rare opcodes carry more information, seem to carry more information that can be used for classification and identification purposes. There are, of course, further directions. I added a few more categorical data when I did the inventorying with IDA. I can still study. I studied this in a two-way contingency table. One way was class, and the other one was opcodes. I could have a third or a fourth dimension for compilers. Compilers may produce a pattern that you should investigate. The 3 or 4 or 5 common compilers. You can start expanding. Common opcode nuggets. There will be a size between basic blocks and isolated opcodes, and of course, try to attack the scheme. Specifically with the purpose of defeating it, which I haven't done yet. Now, if you want to do some related work, I can recommend these 3 papers and so on, and a few more references at the end. A This was more for identification. Let's see if we can find classification. This is work that I did with my honor student Chris Rees, who's now at Vigilant Minds, a year ago or so. So the key procedure here is we run the stuff, we record the API calls, we construct a fingerprint from the API calls, not an ordered sequence, just the mere fact how many times are they called, put them in a database, and then cross-compare it using a similarity measure. The interesting thing was that this relatively simple model, I thought to myself, Chris, we'll start like this, and then if it doesn't work, we'll go to finite state automaton, yielded surprisingly good results. I mean, 80% for a first stab, where you don't have to do very much, it's not bad. I mean, at least for me, it's not bad. Where if the weather forecast was always 80% right, I'd be very happy. High-level overview of how we did this. Data collectors, we build a vector from the API calls. We dump them to the database. We used a comparison, and we then assigned it to a family. Again, the goal here was classification of malware that we knew was malware, but we didn't know which family it belonged to. We wanted to see whether we could classify them just with the API calls. How did the data collection work? We set up, again, fake environments. We faked the network. There was a DNS server and so on, so they thought they were in there. Relayer, we logged the file into the console, so we can have a look at it. What did we do? We used inspiration from the Microsoft Detours project. We hooked the functions. We injected into the process address space. We hooked the functions and just recorded. Okay. I invite you to look at the Microsoft Detours project for more details on this. What is the actual data we recorded? This is an illustration. So it's a vector. Think of a vector, 1,200 elements, and each element tells you the number of calls of a particular call. So find close was called 62 times, find first file A 12 times, and so on. We did this we collected about, the vector was 1,200 plus dimensions, plus dimensions. So each malware specimen had one of those. What we did then is we computed a similarity measure. What is there are many similarity measures. This is probably one of the most common ones. If you remember from high school geometry, what a cosine is, it's very easy to understand. If you have two vectors like this and they're perpendicular, if you project one onto the other, you can't really. I mean, because the similarity will be 0. The more similar they are, the more one will project onto the other, and the higher the score will be. Similarity measure normalized between 0 and 1. So we fudged around a bit with the threshold, and we assigned things to a family if the similarity measure exceeded a certain threshold. these are our results. We collected 77 malware samples, ran them against 17 AV scanners, and then we looked at their classification, then we looked at our classification with our scheme. And with about the threshold of 0.8, that means if the similarity was about 0.8 when it came to this very simple, unordered, just number of occurrence API calls, was about 80%. So our sweet spot was about here. You can see where the discrepancies were for these, for legal and for or MyDoom and so on. We had a few false families. We had a few missed families. You know, as you increase the threshold, the missed family, the missed families, of course, increase because you require more stringent proof. So again, it's a fuzzy factor. Statistics is a fuzzy business, right? The good thing is it makes you more tolerant towards slight perturbations. An interesting side effect, even though intuitively this should be so, but like Oscar Wilde once said, sometimes it's the duty of the intelligent person to state the obvious. It's pretty impervious towards packers. We probably don't use much API calls and so on. We could classify it pretty well, or it well, in essence, it was impervious, and maybe we'll look at this a little bit more. So this is the summary. This simple sequence of API calls was robust towards packers, 80% accuracy, without even putting it into anything more complicated than this very simple database where we cross-compared with this mathematical cosine similarity model. What can you do? Well, you can never be too rich or too thin, and you can never have enough samples, so we should get more malware samples to investigate this a bit more. Again, technique-specific exploits to attack the kind of classification scheme can be run. What we can also do is build a bit more intelligence into the actual modeling of the sequence call using a finite state automaton. And this I learned from Zanero's talk, which was about an hour before. This is how I can hot patch. I invite you to have a look at his classification scheme, which went actually according to a system called arguments, something I hadn't seen done before, so I'm very grateful that I went to that talk. If you want to see related work, you can look at Sekar's work. He actually built a finite state automaton. Strange enough, he stopped. He didn't. I mean, it was a very good approach, and then he just stopped. He didn't really run it on too many things. Rabeck built kind of a whitelist and so on, and Rozanov, that's a master's thesis at the Polytechnic in New York, did this, but statically. So he went to the code, statically disassembled, figured out the API calls, and did a very neat finite state automaton result on this. The final approach, again, so we had fingerprinting on opcodes, we had fingerprinting on API calls, is on graph models. The key idea is here. Represent the program as a graph, figure out some metrics of this graph, and again, construct a fingerprint that can be used in a statistical manner. In order to do this, one has to know a little bit about representing programs as graphs. And here's the whirlwind tour. You all heard, and you all probably did it, a function called an IDA. We can have the control flow graph. So what we first have is a program dependence graph, which includes the data dependencies and the control flow dependencies. So it's an augmented, if you will, control flow graph. This neat little graph from CodeSurfer can serve as illustrative purpose. The green arrows tell you the data dependencies, and the blue arrows tell you the control dependencies. So so sum equals sum plus I is dependent on I here, and I equals I plus 1 is also dependent on I because it updates itself. So the green arrows are the data dependencies, the blue arrows are the control dependencies. The T stands for we take the branch if true. System dependence graph, you can view, if you want the one-liner for this, as an aggregate PDGs augmented with call functions. So now we have everything. We have control, we have data, and we have calls. Calls between these procedures. Again, from CodeSurfer, and I invite you to, I'll have it in the reference, to go and look at the tutorial, 30 pages, and that's all you need to know for the beginning. It's like the 80-20 rule, you get in there. So here we have, again, the same graph. We have our main program, our PDG here, and we have it augmented here with the calls to add, as you can read it here in the code. The main point to get from this is that these programs can be represented as graphs. The statements here are nodes, and the control and data and call dependencies are the edges. The thought here is this: given that this is a graph, and given that there's a rich theoretical literature on analyzing such graphs, and I invite you to look in the reference, read Mark Newman's paper, 2003, 67 pages, and you'll be up to speed. Is that we can find some features of these graphs, and again construct some statistics, and then figure out whether we can use this for classification purposes. Again, this is the most intuitive of the ideas so far. I haven't actually done this yet because I haven't assembled all the tools I needed, but I'm giving you some food for thought. I'm heartened to see that this graph-based approach is not, I'm not the only one who's thinking along those lines. Flake did this last year. He did it this year again in the challenge for RE tools. Then I went to the very nice talk of those UCF students, Sidewinder, who actually used this for reachability analysis. You know, you have a vulnerability down there, you have some sort of entry points, how on earth are you going to get it, and they use a genetic algorithm. Very nice talk. I invite you to have a look at it. A primer on graphs. What do you have to know about graphs? In essence, two things. Well, three maybe. The nodes, the edges, and the edges and nodes can have, actually four things. The nodes can have weights, the edges can have directions. Well, so direction means it has an arrow. This framework is so powerful that very many phenomena in real life can be modeled as graphs. I took here a random sample. You've heard all of the Kevin Bacon game. Kevin Bacon game is nothing but a little graph exercise that you can give to undergraduates. You have also thesaurus. You have telephone networks, internet networks. If you've ever seen that huge graph, you know, it's in essence a network graph. To my surprise, chemistry networks can be done with this: food networks, predator prey, sexual networks, dating networks, whatever you want. The graph paradigm is so simple and so powerful, it can be applied to all these different places. I'll give you a couple of examples what I mean by measures that you can put on graphs. One is centrality. Centrality means importance. If to take something home, centrality just means importance. Now, I'll give you three centralities. There are more. One is degree, and we see here. This is a star graph, and just here for illustrative purposes. The degree centrality says how many nodes are connected to me. So, you know, I count the immediate neighbors. So here we see, you know, everybody has a normalized, you know, 0.25, except for the one here on the outer edge has 0.17 because they only have like two neighbors, and everybody else has three. Now, closeness. Closeness is how close am I from all other nodes. In the star graph, of course, the closest one is the one in the middle, right? It has the highest value because it's easiest to get to every node in there. And the ones with the lowest value in the star graph are the ones on the outer edges. And here, this one here is a bit increased, and this one here too, because the closer you get to the middle, the closer you are to all other nodes. Between the centrality, that's a very nice metric because it conforms intuitively to our notion of importance. Not just how many friends you have, but how important are you to everybody else around you. If you are the go-to guy in your organization, you have a high in between the centrality. It means how important am I to any two nodes. Again, the one in the middle is the most important in this star graph. Not in a graph in general, but in this star graph. Why? All these, if this guy is gone, none of these subgraphs can get to one another. We see the ones on the outer edges are zero. Why is that? Well, because they're not important for any communication. Any two nodes can communicate without going through the ones there. So the importance is zero when it comes to how many paths lead through me. Okay? Now, another measure is motifs. Motifs are subgraphs that are connected, that recur more than it would be normal just by chance. So it's in essence pattern in a graph. We have here a sample of a primitive sample graph, and we have a little motif example. Why motifs are important? Motifs are important because they can give you clues. They're like like fossils for archaeology. If you model processes with graphs and you find motifs that recur again and again, you can well, those were two tautologies in one. You find motifs. They tell you something about the dynamics that drive the network. They tell you something most likely about the generative processes. And they tell you something about if the phenomena that you're modeling is top-down engineered. They tell you something about design principles in them. I'll give you an example. This is a feed-forward loop. This feed-forward loop, very simple. You find this in electrical circuits. For those of you who are EEs, X influences Y influences Z, and X also influences Z. You find this in all sorts of biology, in chemistry. You find this in ecology, engineering, and who knows? We may find this also in our research. If you're interested in this, I'll show you a few references at the end that you can read up on. It's a very hot topic, finding motifs and so on. Okay, so what I was saying is this. Represent programs as graphs and find these measures on them and do analysis. Why do I think this is fruitful? I think this is fruitful because in every other area that I've looked at, and they've done this like in 24 or 20 different areas, but we haven't done it really in a systematic way when it comes to our area. So I think there are some fruitful results that wait there. Related work to this graph-based fingerprinting. Look at Flake's Black Hat presentation in 2005. Mihai is here. He'll be happy to answer any paper on any questions on this here. If you're really a code monkey and very code inclined, read the stuff about interprocedural static slicing. It will give you new perspectives on program dependencies. Flake's talk here for new challenges is nice. And again, as I said, these UCF students who did Sidewinder is also a nice approach because they use a graph-based approach to find this. Okay, if you are interested in what I've been saying, and I realize it was a whirlwind tour, if you want to know more about statistical testing when it comes to this categorical stuff, I refer you to Huberman and Everett. You can get this through your interlibrary loan or Google for some papers, or go to Fravia's lecture on how to get any book for free on the web. For network graph measures, if you're interested in motifs, go to Alon's work. That's very nice. Mark Newman is a nice survey paper, and immodest as I am, you can go to my course on the science of networks if you want. It's a senior level undergraduate course on network and network analysis. System dependence graph, again, if you need a 1-hour introduction, go to the Grama website and read the KISS paper. I've come to the end, and I'm also, my powers that be have sent me here so I can find people who would like to collaborate with me, so I can stick students on certain projects like that, talented undergraduate students. So if you have something that you think is pedagogically useful along these lines or even other lines, I'm open. We can do this. And like with the airlines, I know you have a choice in talks, so I thank you for coming to mine, and I'll be open to any questions.